Now that we've learned about the structure of the proteins and the different functions that they can fulfill, we're going to look at factors that manipulate how well a protein completes its function. One thing for us to keep in mind as we go forward is that how well a protein functions, if it functions at all, is very much contingent on the shape of the protein. Each protein has a very specific folded pattern to it that gives it a very unique overall three-dimensional shape. And that three-dimensional shape is critical for its function. And actually, it's so critical that we have a word that refers to the loss of that shape, and it is denaturation. So the more denatured a protein becomes, the more its shape has been malformed and the less function it's able to complete. And then if it gets to a certain degree, then it's denatured beyond the point of having any functionality at all. So shape is really critical to protein function. Now, there are some conditions that can permanently cause a protein to become denatured and stop working altogether. But actually, small temporary changes in a protein shape is one way that we can modulate the protein. And what I mean by that is being able to turn the protein on and off. So these proteins are completing functions, but you don't necessarily want that function all the time. It's beneficial to be able to say, okay, I want you to do work now, and now I'm good. I don't need the function that you fulfill. And so one way that we can turn these proteins on and off is by having their shape change to a small temporary degree by binding to other substances that are called ligands. Okay, so I think maybe the best way to wrap our head around this would be to just sort of look at this example over here to the right. In the picture, the purple shapes are specific types of proteins that are called sodium channels. And essentially what these proteins do is they just act as tunnels for sodium to travel through. So when they're open, the sodium is capable of going through the channel from one side of the cell to the other, and when they're closed, then the sodium can't move. Okay, so there's this active and inactive form. The inactive form of the channel is when the protein is not bound to a certain molecule, which we call kind of very broadly ligands. So we can see here that the channel is closed, meaning it is in its inactive state. Its shape is in a way where it can't complete its intended function, which is to act as a channel for sodium. However, when the correct ligands bind, then what ends up happening is that there is a small change in the shape of that protein, and it changes in a way that the protein now, the channel is open and the sodium can travel through it. Okay, so this is just one example, but very generally speaking, we have proteins, and a lot of times we will have ligands, which are certain kinds of molecules or ions that bind to specific spots on those proteins. We call these binding sites. And when the ligands bind, it changes the activity level of the proteins. In this particular example, the binding of the ligand is causing the protein to become active, but there are cases where the binding of the ligand causes the protein to become inactive. The general rule of thumb is that the binding of the ligand changes the activity level of the protein, or in a way to think about it is it's kind of turning the proteins on or off. Now, these ligands are very specific. It's not like there's just any molecule that can bind to any protein and turn it on or off. And that's good because we want to be able to have control over when the protein is active versus when it's inactive. And the way that we're able to do that is by having specific ligands that can act upon specific proteins. There's actually a word that talks about the fact that some ligands fit with proteins and some don't, and the word is specificity. So specificity is talking about whether or not a ligand can bind to that protein and change its activity level. If a protein has specificity for a ligand, then that ligand can kind of act as an on and off switch. If it doesn't have specificity, then that ligand will have zero effect on the protein's activity level. It's not a ligand that can control that protein. So if we look at our sodium channel example again, we can see that in this example, there are two ligands that have specificity for this protein. We have the green ligand, and we have sort of this yellowish looking ligand. And both of them have specificity for this sodium channel because they can fit to the binding spot and cause the activity level of the protein to change. However, the red triangle does not have specificity for this protein, so it can't exert any modulating control on it. Now, just because something has specificity doesn't mean that they'll all fit equally, okay? So again, if we look at this picture, we can appreciate that while the green ligand and the yellow ligand fit in the binding site, one of them definitely appears to have a better fit than the other one. And there's a word for this. It's called affinity. The affinity is how good of a fit there is between the protein and the ligand. If there is a higher affinity, it means that there is a better fit. And then if the affinity is lower, the fit isn't as great. And if we say there's no affinity, then essentially it means that that ligand does not fit and it, again, can't exert any modulating control over that protein. So the rule of thumb here, just to kind of throw this in while we're talking about it, is that ligands with a higher affinity will bind more readily to a protein. So if you have a protein and you have equal amounts of two ligands, let's say that I have this sodium channel protein and I have an equal quantity of the green ligand and the yellow ligand. Even if I have equal amounts, I'm going to have a greater rate of binding of the green ligand than the yellow ligand because it has a higher affinity for that protein, okay? Kind of a good analogy for this that I've always liked is I think about jeans that I own. So I always say that I have two sizes of jeans that I technically fit into, one that's a bigger size and one that's a smaller size. And although they both fit, the bigger size fits a little more comfortably. Like there's a little more wiggle room, right? And so if both sets of jeans, the bigger size and the smaller size, are available in the drawer, I'm going to have a tendency to pick out the bigger size because they're more comfortable, okay? And they have a better fit to my body. Similarly, if we have equal quantities of two ligands, the one with the higher affinity is going to be the one that is going to have the higher rate of binding to our protein compared to the ligand with the lower affinity. Okay, so those are some very general rules of thumbs about ligands and proteins. And in general, the ways that we can use these to influence protein activity, we can have the ability to turn proteins on and off, and we can manipulate that by changing how much of the ligand we have, or changing the ability of the ligand to bind to the protein. If we do something that makes it easier for the ligand to bind, then we're going to have a higher rate of binding and we'll be able to manipulate its activity more readily. If we do something that makes it harder for the ligand and the protein to come together, then we're not going to be able to change the activity level of that protein as rapidly. We can also change how quickly the ligand actually gets to the binding site. So we can kind of focus on changing the speed of travel of that ligand to its intended binding site, because once it gets there, that's when its activity level is changed. And then finally, we can also change how rapidly the ligand leaves the binding site, because it's going to exert its control until it detaches, if it detaches. There are some ligands that bind temporarily to a protein and then they release and the protein goes back to its original shape. And there are some that once they bind there, they stay there perpetually and they cause that change in shape to occur long term. So these are just three very broad ways in which we can influence the protein function through ligands. And we're going to kind of dive into some very specific strategies that fall under some of these broader umbrella strategies. The first one is to look at the quantity of the ligands. One way that we can change the ease with which the protein and the ligand come together is simply to change how many ligands are physically present in the environment. So to kind of help us with this, I've got two images here, or I guess two little GIFs that I made. We've got a high concentration of a ligand and we've got a lower concentration of a ligand. Now, the one thing we need to keep in mind is that these ligands are just molecules that are randomly bouncing around in space, okay? They don't have the ability to move directionally with intention. So it's not like a ligand can say, hey, there's a binding spot, I want to go there. Instead, they have this random movement because they have kinetic energy. And as you can see, it's kind of like the game Pong, where they're just like bouncing around, or pinball maybe, where they're bouncing around their environment and ricocheting off at random angles and traveling in other locations. So basically what you're waiting for is you're waiting for these ligands to bounce off of things in the environment and then travel in the correct direction where they end up hitting the binding site of the protein. As you can imagine, when you have a higher concentration of the ligands and there's more of them, the likelihood of the ligand making it to the binding site is higher. When you have a lower concentration of the ligand, it's going to take longer because there's fewer of them, so the odds that they're going to randomly ricochet and bind to that binding site are lower, and so it takes more time for you to get the binding to occur. So typically what we see with ligand concentration and protein activity is that as you increase the ligand concentration, protein activity will tend to increase as well. And this is not a forever increase. We do eventually see a plateau, and that plateau is referred to sort of as that saturation point. At some point, you are going to have so many ligands that the environment will be saturated with them, and they'll be binding at as frequent of a rate as they're physically capable of doing. And once you've reached that point where the binding rate is happening as fast as it can, then adding more ligands isn't going to give you any additional benefit from the standpoint of protein activity. Okay, so yes, an increase in concentration does increase the overall protein activity kind of up into that saturation point. Another thing you can do is you can change the number of proteins, right? So if you think about it, the proteins are kind of the workhorses. They're completing some critical function. And the more of those workhorses that you have, the more quote unquote work you're going to be able to complete in a given time period. So again, just kind of for comparison's sake, we have up here a lower concentration of ligands, and in the bottom we have a higher proteins. And at the bottom we have a higher concentration. We only have 2 proteins up here, and we have 4 in the lower image. Okay. Assuming that there is plentiful ligands for them to be open, which we do have happening in this picture, remember that the intention is for these channels to move these sodium ions across this membrane. Well, only one sodium ion can fit through the channel. It's like a single file kind of deal. And you imagine if you have 2 of these channels open, you'll be able to transport a certain number of sodium ions. But if you had 4 channels, you would have basically double the number of spaces across which to move sodium ions. So you would have a greater amount of activity from that protein overall. So typically what we see is that as you increase protein concentration, you also tend to see an increase in protein activity as well, okay, because you have more proteins completing that function. Now, where this could be limiting is if you run out of ligands to interact with those proteins. If you keep adding more and more and more proteins, but there aren't ligands to engage with them, then you might not get any additional benefit from having more proteins. We don't typically see that occur as often, so we typically say that there's going to be a direct relationship between protein concentration and protein activity. We don't find as many circumstances where that ligand might be limiting. But if it were to be limited, then you would start to see a plateau just like you did with the ligand concentration. So this plateau would occur if you did not have enough ligands. Okay. What we're going to do is we're going to go ahead and stop that there. So we'll call that, part 1, just to kind of keep, again, the videos into manageable sizes. And then we'll pick up with the remaining factors that influence protein function in the following video.